Welcome to Next Level Tutorial. Last time, we tackled the exciting concepts of vectors and scalars and explored the key differences between distance and displacement using an exam question. Today, we're taking it a step further to tackle speed and velocity. But that's not all. We'll also unpack the differences between instantaneous, average, and constant quantities. As always, we'll use real, exam-style questions to bring these concepts to life. You'll master the calculations, understand the theory, and pick up tips to avoid common pitfalls. So, let's jump in and take our skills to the next level. Before we dive into the tutorial, let's take a moment to analyze the question for today. We're working on a problem about speed and velocity. This question builds on the concepts we covered last time, but adds a new layer of complexity. Here, the car travels along two segments with specified distances, directions, and times. The question is divided into three main parts. First, we calculate the resultant displacement of the car, which is what we did in the last tutorial. Then, we move on to calculate the average speed for each segment and the entire journey. Finally, we calculate the average velocity for the first segment, the second segment, and the entire journey. There are a few key points we need to focus on. First, scalar versus vector. As we've learned before, displacement and velocity are vectors, while distance and speed are scalars. Be sure to identify whether the question is asking for a scalar or vector quantity, as this will determine how we approach the solution. Second, entire journey versus specific segment. Pay attention to whether the question is asking for the quantity related to the whole journey or just one specific segment. Each requires a different calculation method. Third, average versus instantaneous. While this question focuses on average quantities, it's important to distinguish them from instantaneous quantities, which are tied to specific moments in time. With these focus points in mind, let's get started and break this question down step by step. Let's start by understanding the difference between speed and velocity. Speed is a measure of how fast an object is moving. It's a scalar quantity, which means it tells us only the magnitude, how fast, but not the direction. The calculation for speed is straightforward. It's the total distance traveled divided by the total time taken. This represents the rate of movement. Using symbols, speed is denoted as v, which equals d, the distance traveled, divided by delta t, where delta, the triangle symbol, represents the change in time. It's important to remember that speed, as a scalar, focuses solely on how fast an object is moving, regardless of the direction. For instance, imagine a car traveling from point A to point B along a winding, curvy road. Even though the car's direction may change multiple times along the journey, it can still maintain a constant speed throughout. This highlights that speed depends only on the total distance covered and the time taken, not the path or direction of motion. Now, let's move on to the concept of velocity. Velocity is similar to speed, but there's a key distinction. While speed focuses on distance, velocity is concerned with displacement. Displacement refers to the change in position from the starting point to the ending point of an object's movement. Since velocity is defined as the rate of change of displacement, it is a vector quantity, which means it accounts for both magnitude, how fast, and direction, where. The formula for velocity is displacement divided by the time taken. Using symbols, velocity is written as v, with the small arrow above v indicating that it is a vector quantity. This is expressed as v equals vector s divided by delta t. This emphasizes that velocity always includes direction as part of its definition. To illustrate the importance of direction, imagine a car traveling along a circular path at a constant speed and returning to its starting point. While the car may have traveled a certain distance, its total displacement is zero because it ends up back at the same position. As a result, the car maintains a constant, non-zero speed throughout the journey, but its average velocity is zero. This example underscores the fundamental difference between speed and velocity. A journey can have a positive speed, but zero velocity due to the difference between scalar and vector quantities. When working with velocity, always remember to consider both magnitude and direction. Both are essential for accurately defining this vector quantity. Now, let's take a closer look at the difference between instantaneous and average quantities, using the example of circular motion. First, let's redraw the diagram of the circular motion. We'll first label the directions, upward being north. Imagine a car traveling in a circular path, starting at point A and returning to point A after completing the loop. Let's also label the quarterway points along the journey as B, C, and D. Suppose the car is moving at a constant speed of 10 meters per second. Now, let's focus on each point along the path and determine the instantaneous quantities. At point B, the speed is 10 meters per second, as defined. Since velocity also considers direction, the velocity at point B is 10 meters per second to the east. At point C, the velocity changes direction to 10 meters per second to the south. At point D, the velocity is now 10 meters per second to the west. These are examples of instantaneous quantities, as they describe the values at specific points along the car's path. In this case, the magnitude of the speed is constant at every point, but the direction of the velocity changes depending on the car's position. Now, let's shift our focus to the entire journey and examine the average quantities. Once the car completes the circular path and returns to point A, the average speed for the journey is still 10 meters per second. This is calculated based on the total distance traveled divided by the total time taken. However, the average velocity for the journey is 0 because the car's total displacement, its change in position from start to finish, is 0. Dividing this 0 displacement by the time taken results in an average velocity of 0. This highlights the key distinction. Instantaneous quantities describe values at specific points along a path, while average quantities are calculated over an entire journey or path. Now, let's return to the extended question we introduced at the beginning of the tutorial. It describes a car traveling in two different segments. In the first segment, the car travels 60 kilometers north in 1.5 hours. In the second segment, it travels 80 kilometers east in 2 hours. To make this clear, let's start by drawing a diagram. First, we label the directions, upward being north, for reference. The car starts from an initial position, which we'll label as point A. It then travels north for 60 kilometers, reaching a new position, which we'll label as point B. The distance between A and B is 60 kilometers, and the time taken for this segment is 1.5 hours. From point B, the car changes direction and travels east for 80 kilometers, reaching a final position, which we'll label as point C. The distance between B and C is 80 kilometers, and the time taken for this segment is 2 hours. This gives us the full journey of the car, consisting of two segments, A to B and B to C. Now, we'll calculate total quantities for the entire journey. The straight line distance between points AC is 100 km, which we have already calculated in the last tutorial. The total time taken for the journey, let us call it delta T ABC, is the sum of the time for each segment, which is 1.5 plus 2 is equal to 3.5 hours. Next, we need to calculate the direction for the vector quantities, specifically the resultant displacement. To determine this, we calculate the angle theta between the resultant displacement vector and the northward direction. According to our earlier calculations in the previous tutorial, this angle is 53.13 degrees east of north. With this information, we're ready to proceed with calculating the required quantities for this problem. Before jumping straight to the answers, let's calculate all the quantities for each segment of the journey, as well as for the entire trip. First, let's focus on the journey from point A to point B. The distance AB is 60 kilometers, and since the car is moving directly north, the displacement AB is also 60 kilometers north. The time taken for segment AB is 1.5 hours. The average speed AB is calculated as distance AB divided by delta T AB, which is 60 over 1.5, giving us 40 kilometers per hour. The average velocity AB is calculated as displacement AB divided by delta T AB, which is 60 kilometers to the north over 1.5 hours, resulting in 40 kilometers per hour to the north. Next, we move to the journey from point B to point C. The distance BC is 80 kilometers, and since the car is moving directly east, the displacement BC is 80 kilometers east. The time taken for segment BC is 2 hours. The average speed BC is distance BC divided by delta T BC, which is 80 over 2, giving 40 kilometers per hour, just like the first segment. The average velocity BC is calculated as displacement BC divided by delta T BC, which is 80 kilometers to the east over 2 hours, equals to 40 kilometers per hour to the east. Now, let's consider the entire journey ABC. The total distance traveled, which is distance ABC, is the sum of the distances for each segment. 60 kilometers plus 80 kilometers equals 140 kilometers. The total displacement ABC is the straight line distance between the starting point, A, and the final point, C, and with the direction. According to what we calculated earlier, it is 100 kilometers at 53.13 degrees east of north. The total time for the entire journey delta T ABC is the sum of the time for each segment. 1.5 hours plus 2 hours equals 3.5 hours. The average speed for the journey is based on the total distance and time, which is distance ABC over delta T ABC and equals to 140 km over 3.5 hours, giving us 40 kilometers per hour. The average velocity is determined using the total displacement and the total time taken. To begin, we calculate the magnitude of velocity for the entire journey, ABC. To represent the magnitude, we use absolute value signs. The magnitude is the total displacement divided by delta T ABC. With a total displacement of 100 kilometers and a total time of 3.5 hours, This gives us 28.57 kilometers per hour. When combined with the direction, the average velocity for the entire journey ABC is 28.57 kilometers per hour at 53.13 degrees east of north. It's important to note the difference between distance and displacement in this context. Distance refers to the total path traveled, which is 140 kilometers in this case. Displacement, however, is the straight line distance between the starting and ending points of the path of focus, which is 100 kilometers. The average speed is calculated using the total distance, while the average velocity depends on the displacement. For vector quantities like velocity, both magnitude and direction must always be considered. For our own learning, it's important to recognize that the speed and velocity we've calculated so far are average quantities over various segments of the journey. These are not the instantaneous quantities, which represent values at a specific location or point in time. In this case, there isn't enough information to calculate the instantaneous speed or velocity, as these values could vary during the journey depending on factors like acceleration or changes in direction. With this breakdown, we've covered all the necessary calculations for the question. In this tutorial, we explored the key concepts of speed and velocity. We learned the difference between speed as a scalar that measures how fast and velocity as a vector that considers both magnitude and direction. We also distinguished between instantaneous and average quantities, using examples like circular motion and multi-segment journeys. Lastly, we solved a real-world problem, calculating average speed, average velocity, and resultant displacement for a two-segment car journey. And that's not all. Stay tuned for the next video, where we'll explore the topic of acceleration to take our understanding of motion to the next level.